Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is element-based differential relay testing for transformer and bus protection applications using Megger RTMS. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenters today are David Beard, Relay Applications Engineer, and Sugosh Kuber, Relay Applications Engineer. Also, to assist with the question and answer session, we will have joining us Abel Gonzalez, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, David.
Okay. Thank you, everyone. I'm glad you guys were able to make it today. I know that some areas it's a little hotter than most. Some areas we're a little bit busier than most. So greatly appreciate everybody's attendance today. And we will get into this and show you a few little cool ideas on how to test for transformer and bus differential protection. We will go over differential protection, just kind of a basic overall operation of how the differential protection works. The slope characteristics, will define those and just kind of give you a little bit of an understanding of the slope characteristic itself. The relay I'm going to be testing on will be the GE BDD relay. It's a very nice and unique relay. I like this electromechanical relay for a number of reasons, and we'll get into those as we proceed further. The bus protection operation will be taken up by my colleague Sugosh, and he'll run through the bus protection requirements along with the high impedance bus differential protection. And the relay he will be testing today will be the GE PVD relay. And then, of course, summary and answer as many questions as possible at the end of the webinar. So as we get started, it's kind of nice to know a little bit of a differential operation principle, right? So if you guys have seen multiple webinars that we've had previously, we talk a lot about the same concepts, but in the end, it's the concepts that actually drive the relays, and knowing the concepts very well allow us to test these relays thoroughly. And the current differential relay works on the Kirchhoff's current law principle. So at any given node in a power system network, the amount of current that's going to enter this node is going to equal the amount of current that actually leaves the node. When there's a difference in the current vectors from one side of the protected zone to the other, then the differential condition will exist, and you'll start seeing some differential current flowing down into the relay section that we would actually have here. And what actually makes a little bit better sense is we're going to check this out now. So what we did is come up with a little bit of a explanation on how this works. So we're going to see what's going to happen when we have a fault outside of the protected zone, and when our currents are flowing into our CTs, as they are set up in the design of the substation and then through our transformer, we're going to actually see that ideally there's no operate current here. Why is that? Because we're actually given through fault current that's coming into the protected zone and it's leaving the protected zone. So we don't have any change in direction of current. So therefore, we will not see any type of trip. Now, here the current can be increased sometimes by a factor of 10 or more, and the polarity of the current can stay the same. Therefore, there'll be no differential, right? So when we get to an area where we have an internal fault being inside the protected zone of the relay here, our currents are flowing almost in the same direction, but they actually turn around and come back to feed this fault, right? So when we run the currents on the secondary side, they change direction, and then this current adds up at the summation point that you're going to see here at these nodes. And once this current adds up, the differential current adds up, it goes across the relay, and then the relay issues a trip, right? The current in the operate coil must be greater than the slope current when it's compared to the restraint current calculation. This condition will hold true as the relay sees the internal fault and trips on a differential condition, right? But does this mean that there any difference in current that we should immediately trip? And the answer is no, because if we had even during normal operation, you have a lot of mismatch and errors that are happening within the circuit itself. You have relay accuracy errors. We also have errors in the CT. We have a little bit of error in just the cabling. So all these little errors add up to be some small value of differential current. So you will always see some differential current across this relay. But whenever we have external or normal operating conditions, external fault or normal operating conditions, we will see a little bit of differential current in this section here, or in the relay, I mean. So why do we use the differential restraint? Why do we use the restraint differential? I mean, so our operate, these are some basic calculations that you will see in manuals. Specific relay manuals have specific calculations for the operate and the restraint. You have your percent slope calculation, then also you're going to have your operate, which is going to be greater than your slope percentage times the restraint current. Okay, these to understand this concept, it makes it easier whenever we actually go through and start doing a little bit of testing. You can physically see what these calculations are calculating in front of you, so it gives you a better picture. And that's another reason why I really like the electromechanical relays, is because you can actually see what's actually going on. Now we're going to briefly run over the slope characteristic. So in the slope characteristic, defined by the calculations of the operate and restraint current, were based on analog current signals, right? We're going to read the relay from both windings of the transformer, and then we're going to have a minimum pickup point for the operate current setting. Then we're going to have the characteristic is going to be divided into two regions. We're going to have an operate region. We're going to have a restraining region. And then the characteristic will also have at the top will be our instantaneous value. So at some point when the current gets too high, we have to just completely shut the system down, right? Because now we're getting into a complete whole nother situation. So we do have to have some minimum pickup value. The slope here is actually going to be it's adding, where this comes from is we're actually adding or summing all of the errors together that are within the system. So you might have some magnetizing inrush error. You're going to have the CT error that we talked about, the relay error, its accuracy error, and all these errors add up. And then once we get all the addition of those errors added up, then we can calculate a setting that works very well for the slope. So we can cross this, once it crosses this threshold, the current does, then we'll operate for an internal fault situation. So the restraint characteristic can be divided into two areas of protection. We have the tripping and non-tripping, which will be the operate, non-operate. And then we also have the steady state and proportional compensation errors. And this is what I was talking about again with the CT accuracy errors that still play a role in the way this slope is actually calculated and where we need to be set to. The load tap changer and node load tap changers for tap changing transformers, those are errors that need to be added into this. Your tap mismatch, depending on your CTs from your high side and low side of your transformer, those errors have to be applied into this mismatch as well. And then also your magnetizing current, which we said the overexcitation, and then the slope. And the slope can usually range somewhere between the 15 to 45% range. In the electromechanical world, we had predefined settings. So you would have a couple of tap screws inside that would dictate it was either 15, 25, or 40. Nowadays, in newer relays, we can fine tune this. You can actually make these a little bit more precise, a little bit more accurate. And as close to those settings as possible, so we don't have a huge amount of error that we used to with the electromechanical relays. And then we also have the unrestrained value, which is clearly, internal fault. So the harmonic restraint method is used to make sure that the differential scheme does not nuisance trip. When we energize a transformer, the scheme should also protect the transformer from any kind of internal faults. Lost my pen there. Okay. So where are we getting this magnetizing inrush current? Well, it's coming from energization of a transformer after a complete de-energization. So you need to know where the actual what point in the sine wave did the transformer get de-energized, and then now we're going to re-energize it. Might not happen at the same point that the transformer was de-energized the last time. That can be an magnetizing inrush current. Post-fault recovery voltage, or post-fault voltage recovery, which would be after we have a fault, we got to close back in on the transformer, get the system back online, so we can also have a high inrush current there as well. And then energization of a parallel transformer that's in the same area as the first transformer, we can get some remnants of the high magnetizing current is in there as well. So we have a lot of different scenarios that can play out here. The other one is too, that I don't have listed, would be, depending on where it's at in the system. So if your transformer could be closer to the generator, there's not a huge amount of resistance between the transformer and the generator. So at that point, you could see a very high amount of current for a longer duration of time. So when the more resistance that you put between the transformer being energized and the source will allow the inrush current to not be so high. It'll actually, and it also helps it decrease the amount of current that's actually flowing through the relay as well, depending on if it's farther away from the source that it's being energized from. So there's a lot of different factors in there that can take place that we could actually get some remnants or be affected by the harmonic restraint or the harmonics or inrush of the transformer. The inrush currents are usually higher magnitudes. Again, depending on where it's at in the system and where it's being energized from, those currents could be in excess of 10 per unit, or it could be less. The duration of time between the decaying sine wave of the magnetizing inrush is also dependent on the placement and where what else is affecting the transformer at that time when it's in the system. Also, it also tells us that it's not an internal fault. It isn't an internal fault, but it pretends like it is an internal fault. So that's what we want to do, is we want to make sure that we block for this rich harmonic content that's coming out of this transformer when we energize. And then the operating current can always be higher than the slope, then yet can cause a false trip, because we're not, if we didn't have any type of harmonic restraint to see this DC component in the inrush, then what will end up happening is we end up tripping, and then we'll constantly run that same cycle again. They'll try to energize the transformer, then the relay will still give them another trip, and then we'll just go back and forth, and you just sit there and just energize a transformer for no reason, and could likely damage the unit as well by constantly banging it around. So in the electromechanical, it's kind of different. We're kind of jumping off a little bit, but previously, after we kind of just get an overall general idea of these different types of elements that we need to watch for and actually test for, that's when we come over to the actual relay portion. And this is where we're going to start looking at the BDD relay that I have selected for this. So in the BDD relay, what we're looking for is a few things. We want to make sure that once we do our testing, we get all the proper nameplate information. We want to make sure that we have the right instruction leaflet. We want to make sure we have the right model number of the relay that we're actually testing, and then make sure we're on the right relay type. So these relays, the General Electric ones, used to look very similar. So you could confuse this relay very easily with the General Electric STD. I'm not saying anybody got STD. I'm just saying that we have the STD itself, and then there's a BDD 16, 17, 18, and a 15 as well. Where's my pen? Okay, the slope of a relay. So this tap plug that you're going to see here goes into 15, 25, and the 40. Those are our predefined slopes. And those predefined slopes there are the ones that I was talking about earlier. We can actually fine tune whenever we have a newer style relay. And our DC voltage for powering this relay up as well, which would be the 125 or the 250 volt DC, depending on what this relay actually needs. So each one of this is the tap block for the BDD relay. The first one is winding, will be winding number 1. So this is for the first winding, and these are individual taps that can be set for your mismatch between high side and low side of the transformer. The second set of windings is for a second winding transformer, 3 winding transformer. The one that I currently have here that I will be testing on is a 2 winding transformer. So this third winding doesn't exist. But if you did have one, then you can actually see that you still have the same amount of screws, the same amount of windings here as well. And then they will be labeled on the side of the relay itself. And then you have the tap screws, like I said, for the taps. And the other one is this guy. Don't use this as a tap. It doesn't work. I've seen people, not people, but I've seen relays that I've went back and actually did testing on, that this screw right here is to hold the bar in place, the tap bar in place. And I've seen this being used as an actual tap. And that is not correct. These are thumb screws, and they have a little bit bigger head on them that you can actually put them in there with your fingers and hand tighten them. If you decide that one day you want to tighten these up a little bit with your inspection that you do on your electromechanical relays, and you twist this guy just a little too much, then he's going to end up breaking this head off. That's a bad day. I'm not going to lie to you. This is when you pull this tap out and you put it in this relay and you twist the head off of it, then you need some tools because you're going to be in panic mode at that point in trying to get that screw out. The GE or the BDD relay, here is the diagram for the actual relay. It comes out of the manufacturer's IL, and this is what we're going to use to connect to. And here I am using the SMRT 46D unit. I'll let you guys sit on this for a minute. We are actually coming in with each individual winding. Again, I do not have a 3 winding transformer, but if 3 winding relay, if you do, you can come in here and use this third channel that's in the SMRT unit, and then you can still use the first 2 for your winding 1, winding 2. A battery simulator from the top is going to come down and connect to give us power for the relay and for the trips. And then also we have our binary input, which I have selected 1. You can use any one of the 10 binary inputs that are available on the unit itself. So the things we're going to test, we're going to test the pickup, we're going to test the slope, and we're definitely going to test the instantaneous value. Now, another thing we're going to test too is the harmonic restraint. right? Because we still have the inrush capability, and this relay is here to block for that condition, but we still need to make sure that it tests well. This kind of giving you an overview as well. When we're testing the BDD or any relay, as a matter of fact, we have a wide range of product selection. We have the Smart 1 series all the way down to a mixture of 3-phase units with 3-phase with a display, non without the displays, and they all utilize the same software. So the same software I'm going to show you here in a moment is going to be the same software that you can use to drive any of these products. Okay, so we're gonna go Artemis. So this is what we have here. I need to get down to this guy. Okay, so where am I at? So for the BDD test, this is in RTMS. Okay, this is a test plan that's inside RTMS currently. If you come into this library test button, you'll select GE, and you can come into the BDD relay, and this will be this test plan that you're going to see here. All right. Now, if you notice too, you have 3 winding tests. Well, even though my transformer relay only has 2 windings, doesn't mean I have to try to run all tests. It just don't run these tests, right? You can also have these tests not being enabled, which they will not be displayed here if the settings are not available for that 3rd winding as well. So in here we'll have the first winding pickup. We'll do a second winding pickup. We're going to do the restraint pickup. We're also going to do the instantaneous and a harmonic restraint. So the first one is just going to be using the our ramp screen. We have our advanced ramp screen. We're going to give it the value that's going to be a little bit less than the pickup value of the relay tap. And on the BDD nameplate itself, it'll have the tap value, and then on that nameplate will also have the pickup value. And so that's what we're going to use. We're going to use that pickup value, which on this case is 0.30, and we're going to take it times the tap value and give us our values for us to run our pickups on. And we're starting at some value below pickup, and then we're going to ramp into the pickup until the relay operates. So let me get my relay sitting. Okay. So we're going to go, run, and you'll notice that the test itself is going to start ramping. And once this ramps and the relay actually sees that pickup, that's whenever the relay is going to operate, and then that gives us our pickup of that winding. Right? Okay. So I ended up with 1.447. Relay's a little bit off. That's okay. We're going to come in here and look at the report for that. I expected the 1.5 because I didn't even show you. Let me go back and show you one. We need to go to the settings of the relay itself, which I have in here already. So our settings for our relay are going to be the winding 1 and winding 2 taps are going to be for 5 amp taps is what I have them screwed into. The DC voltage for powering this relay up is 48 volts. I like to go on the lower end if I'm bench testing. And then our instantaneous, of course, is 10 to 8 times the tap winding. In this particular relay, it's 10. And then the slope percentage here is 15. It's where my screw is. And then the harmonic restraint, which would be the factory 20. That normally comes standard with the unit, with the BDD. This, when I come in to do my first pickup, you'll notice that here is the report for the pickup. I'm expected at 1.5, which is the 0.30 of tap, right? So we ended up picking up somewhere around 1.5, 1.4, 44. We got a minimum, maximum values. We are allowing the 10% error. Again, this error comes from the manufacturer's instruction leaflet, or if you have some company requirement that says that all electromechanicals are this and all microprocessors are this, then you would just add that information in here, and then we'll calculate the error for you. Okay, so we're going to come in and do the next test, which is the pickup test for winding 2, right? So I was able to keep my connection the same for the winding 2 piece. And then we're going to get into the test. And we're going to run this test, right? So winding 2. So I'm on winding 2 here. We're going to watch it increase, and then we're going to wait until the contact closure happens on my relay. So as it's coming up, it's getting close. All right, we got contact closure. Now we're reporting the information. So 92, and then we're coming and check everything out in our single page report, which is nice, 1.49, and we're very close on that guy. But this is basically how we're actually running these tests. You ramp up to a certain specific test value, and then you ramp back down, and then that's it. That's what we're doing. So you got to remember the second part of it is that the winding is also, there's nothing on the first winding, so we're hitting that minimum pickup mark is where we're actually hitting in our slope characteristic slide that I was showing earlier. We'll come in and do the restraint winding for 1 and 2. So we're going to select that, restraint winding 1 and 2. We're going to go into the test. And for the 5 and 5 tap, out of the instruction leaflet, we have values in there that we're applying. We're applying one at 0 degrees. We're applying the other one 180 out as it would be connected into the system. And then we will hold one value steady, one winding steady, and then we will ramp the other winding as if an internal fault was happening. Okay, so we will actually hit the run, and again, we're still waiting for contact closure here on the top for our relay. So our relay is getting close. All right, well, that's a little off, but it's okay. 2889, so we'll come in, look at the single page report. All right, so now we have our expected slope percentage. We have our winding 1 is what we're actually holding that value to, and then we're ramping the winding 2 value, and then we measured at 28.8. So we're a little bit out, but you know, I mean, it's an older relay. It isn't going to roll out perfect like it's brand new. We measured the slope, and we're within specifications between the minimum and maximum, so we get a green check mark. Right, second to last test, instantaneous test. So I'm going to change a connection here for a moment. Mr. Mike.
Yep. And so we can capitalize on our time here. We're going to fill this little intermission with a question from our audience. I'm going to direct it over to Abel Gonzalez. Abel, when testing the slope of a 3-winding transformer relay, do I need to perform a slope test using the 3rd winding as well?
Hi, thanks, Mike. Can you hear me?
I can, yes.
Okay, thanks, Mike. Thanks, guys. Well, the answer is of course you need to test when you have a relay and you have 3 windings, like the relay that David was showing there. If the 3 windings are being used, I mean, if the 3 elements are being used, because you have, like you say, a 3 winding transformer, then you need to test all the elements that are enabled in the relay at the moment of the testing. Remember why you are testing. You're testing to verify the proper functioning of the relay, and you only get a few opportunities to test that relay during the lifetime of the relay. So when you're there and you have the opportunity to test the relay, you're in front of it, you're supposed to test all the different elements that the relay has enabled. Now, it's not enough to test winding 1 versus winding 2. You would need to test the operation of the 3rd winding. Typically, you would do on this type of relay, you can do 2 tests, winding 1 versus 2, winding 1 versus 3. If you want to be thorough, you can go ahead and test winding 2 versus 3, but typically you will only need to do the first two tests that I just mentioned. Back to you, Mike.
Cool.
Thanks, Bill.
Yeah, thank
We'll
you,
let
sir.
David take it from here.
Yeah, I apologize. It just took just a little bit of a second to get everything rearranged for this guy. So the instantaneous pickup test, we're still doing the high current for the instantaneous, and we're going to run this test. It's going to be a pulse test. We're pulsing a value underneath the actual pickup value, right? And we come into it. Another thing I like to always say too is when we're doing any type of test, we want to make sure that our ramp or pulse duration starts before the tolerance. So if you're looking for a 10% tolerance in your relay settings or in your test, then we want to make sure that we start our ramp before that. So it could be 15% or just somewhere outside of that tolerance band, because you want to make sure that you're actually getting proper test on it and you're covering your basis with your tolerance levels. Okay, so we came in, we did pickup value, relay operated at 49.75, which is not bad. And then we expected here, we got a minimum and maximum value of 10% over. And again, we started a little bit outside the 10% factor. And then that way we were able to get a good test out of this guy. It's not bad for being an old relay, I say. Last and final test, harmonic restraint. Oh, this everybody loves this test. Okay, so let's get in here. So what we're going to actually do, what's really nice about doing harmonics test with RTMS and an SMRT unit is that we don't have to do using two generators, right? You don't need to stack two generators, so we don't need 4 cables to tie to this relay. We can do everything that we need to do using the single current generator, right? So we have the single current generator is going to apply our fundamental frequency along with 120 hertz signal. It's going to be stacked on top of the fundamental frequency of 60. So you'll notice that if you see this little guy right here, his little icon looks like a sine wave, and that indicates to me, the user, that you have 2 sine waves stacked on top of each other. Okay, so now this one speeds up connections because I don't have an extra connection to make. 2, I can perform everything with just a minimal amount of connections, and if I play my cards right, I can actually get all my connections on there for one specific relay and never have to make those changes, right? So we'll run this test here. So again, it's a value below the actual setting that we have. So we're going to hit play. We're going to get our relays going to start taking off. And we are holding the 120 hertz frequency steady, and we're ramping the fundamental frequency, not the frequency, we're running the current, the fundamental current for that frequency. And we're going to wait till this relay gives us an indication that says yay or nay. I hope it's a yay. Hope it's a yay. I don't want to. These relays are pretty stout. They've been around for a very long time. So it's really nice to see that when you get one that actually you can hang on to, really works very well. It's pretty nice. Okay. What do we get? They did not operate. Okay. We operated there. Let's run this test again. Let's see what was going down. Maybe I didn't see my. Let's roll it again. Okay. We're getting in there again. And just like, you know, sometimes you need to run a few things a little bit. Sometimes you got to adjust your debalance contact for the relay itself. So, did not operate. Okay, what's happening here? Oh, it did operate. Okay, it didn't operate for that one. Something went a little awry there. Okay, so we actually do have values, which is what I put in. Fundamental frequency of 9.28 is where we actually operated on. The harmonic content was held steady at 1.88 at the 120 hertz. And then we have the minimum and maximum values and then we have actual harmonic, which was calculated from these two values here. So we are within range. Okay, good. All right, that is all for the transformer section. I'm going to turn this over to my colleague, Mr. Sugosh, and he's going to run through the bus protection portion.
Thank you, David. Good afternoon, everyone. Michael, can you see my screen?
Yes, sir.
Okay. So in the second half of the webinar, I'm going to talk about the bus differential protection. So what I have here is a simple representation of the bus differential scheme, right? Like David explained before, the differential protection works on principle of KCL. So what I have here is the source side. I call this as a source side, the main breaker that is feeding into the bus here, and it has multiple feeder breakers feeding the rest of the loads here on the load side. And I have a relay that is connected to the CTs on both the source side and the load side. You can observe that the CTs are parallel from each circuit breaker. And of course, what I'm showing here is only the single phase representation of the connection diagram. Okay. So when we talk about differential, we would want to establish something called as a zone of protection, right? So in here, this colored area shows the zone of protection for this particular differential scheme, right? So and that zone of protection is defined by the location and placement of these CTs. So anywhere, if the fault lies anywhere within this particular zone here, it's considered to be an internal fault to the zone of protection. So like David explained about the KCL before, any difference in current that is entering and leaving the bus, right? Let's consider this bus as a node. So any difference between the source side and the load side, there is a current difference, and when that current difference is above the threshold setting in the relay here, then there is a fault present inside the zone of protection. Now, the way this relay should operate or should behave is that, of course, for any fault that is external to the zone, let's say we have fault here somewhere outside after the CT location, or somewhere it's external to the zone here, we do not want this differential relay to operate. We want the other backup protection to take care of those faults because they are external to our zone that we just defined. And then, of course, during the nominal load conditions as well, we want the scheme to be secure and not nuisance trip. And for internal fault, of course, the relay should operate. So this is the basic principle of bus differential protection. Now let us move on to the requirements of bus protection. So when there is a fault on a bus bar, when we talk about the faults on a bus, these faults are pretty much of high magnitude. So if the CT sizing is not properly done, then there are chances of these CTs saturating for these faults. And when CT saturates, of course, there are chances that the scheme may maloperate. So some of the schemes under bus protection, they require the CT sizing, the ratio, them to be same. That is one of the requirements for some of the schemes used under this. And no matter what, in the bus protection scheme should be able to differentiate between true faults and false differential current. So by saying false differential current, what I mean is that these type of currents can be caused by CT saturation, which happens because of an external fault. Now that is why we call it as false differential, because we just established the fact that when there is an external fault, we don't want the relay to trip. So there is a false differential there. There is a difference, but it's not the true differential current. And next comes the security of the scheme operation. So the bus bar, a substation bus that connects various entities on different voltage levels, all the way from generation, transmission to distribution, all the way from industrial loads to residential loads. So when these faults occur on a bus, it can jeopardize the stability of the system. And when there is an outage, it can be on a large scale. So the security of the scheme operation is of high importance. And last but not the least is the high-speed operation. So we just spoke about how faults on a bus bar can be of high magnitude. So of course we want these faults to be cleared as soon as possible. So the scheme must operate with a high speed. Now let me talk about specifically about high impedance bus differential protection. So this is one of the commonly used and popular types of bus protection scheme, and this is popular among the electromechanical relays and been in use for many years, right? So as the name suggests, so high impedance relay, it has a very high impedance to the flow of current. So this particular scheme, like I was mentioning before, it requires that the CTs, all the CTs that are used in the scheme, they should be of same ratio. And of course, the CTs are parallelly connected, and then to the relay. We have to make sure that the polarity connections are done correctly, such that the currents are adding up to zero whenever it's a nominal load condition or external fault. So whenever there is a difference of current because of an internal fault, this current difference is seen by the relay, like we discussed before. And you know, there are different types of this scheme implementation. You can also see that there can be like a voltage-based setting present on a relay. Even though the difference is in current, the relay uses the voltage drop across the relay to monitor the condition, whether it's a fault or an external fault. So like we were talking about the CT saturation challenge, you know, even a smallest of a current difference can cause a relay to trip. The performance of the CT becomes very important, right? So it's important that we need to choose the right type of CTs with similar accuracy ratings and similar performance characteristics, and all these CTs should have a high knee point voltage. So these are some of the pointers about high impedance bus protection. So next I'll be talking about the actual operation of this type of scheme. So in this figure here, this figure depicts a high impedance bus differential relay that is used here. Let me get my pointer back. Okay, it's used here, and you can see that it's parallelly connected with the CTs in the scheme. So what I have here is a high impedance component that is usually resistive in nature and is connected in series with the relay element. The value for this high impedance element, it can be somewhere in thousands of ohms. It can be at 1 kilo ohm or 2 kilo ohm, just depends on that relay. And along with this, what we have here is a varistor that is included across the measuring pad. So I call this as a measuring pad. So any differences that these two sites are seeing, that currents can be forced through this pad, and that's why I term this as a measuring pad. And we have this varistor across this pad so that it can protect the relay and CTs from being damaged due to high voltages. You can see here that this point is grounded here so that it prevents harmful voltages appearing across the circuit. So like the name suggests, because of this high impedance component, no current would want to flow through the relay during any condition, ideally, right? But whenever there is a significant current difference between the source side and the load side, and that happens because of an internal fault, right, in our zone of protection, this current is forced through this path, and then it's seen by this high impedance relay. So because of this current here, there will be a voltage drop across this relay here. And since I mentioned about a voltage-based setting in a relay, in this type of a relay, it actually checks the measured voltage drop with regards to that setting. So if the drop is more than the setting, which means that there is a presence of internal fault in this particular system, right? And then the relay should trip. So it decides that based on the voltage that is seen. So that is the the principle behind high impedance bus differential operation. Now let us delve into different scenarios as to what happens when there is a particular type of fault, or what happens with like a normal load condition. So here I have shown a nominal load condition where I have the source side and the load side here. The breakers are closed. You can see these currents, the 1000 amp current flowing through the main, and the feeders are drawing an equal amount of current, all the 4 feeders. So you can observe that the CT ratios are all same in the scheme here, like we discussed before. And let's look into the secondary currents of these CTs, right? So for the main CT, main breaker CT, the secondary current is 2.5 amps based on the current and based on CT ratio. And then we have the secondary currents for the feeders as well. It's around 0.625 amps roughly. So you can of course say that these are equal. So when you add these feeder currents up, of course they're equal because the currents are same on the primary side as well. So this means, of course, there is no difference in current at 0. And then because there is no difference in the currents, there would be no voltage drop across this relay. So, the relay is a happy guy. He doesn't have to work at this moment. Now, when we talk about the external fault scenario, let's see the fault here. So we have the fault here, which is external to the zone that we established. So when we have this high magnitude fault, of course, even when there's a fault, the currents are still feeding onto the fault. So whatever current is being entered to the bus is still leaving the bus. So there is no differential ideally. But what happens when this high magnitude fault happens, and what happens to the CT is the question. So there is a chance that this CT can saturate because of that high magnitude fault, and because of which, the reason it saturates is that because it carries the most current in the circuit at the time of the fault. And because of this saturation, it will definitely see some current differences on the secondary, right? And because of which we will see some differential current, even though it's very small. It's let's say in this example, it's around 0.05 amps. Now let us establish some relay settings here, information. So let's say my voltage setting, threshold setting on the relay is 200 volts. Okay. Now and let us say the high impedance component is around 2 kilo ohms for this particular relay. So based on that, now the actual voltage drop that the relay is monitored is around 100 volts. So of course, in this case, because it's an external fault and the voltage drop has not still crossed the threshold point, there shouldn't be any trip from the differential relay perspective, right? So the differential will not trip in this case, but still this fault will still be cleared by the backup protection or the overcurrent protection on this feeder, right? So it trips this breaker open and clears the fault. Okay. Now let us look into the case of an internal fault. So for an internal fault, let's say I have a fault on this bus here. Again, it's internal because the zone we have established. So all the sources in the system would be contributing to this total fault current. So similarly, the secondary currents, they add up and they are forced through this measuring path of the high impedance relay. So what happens then is that there is a voltage drop, right? Because of this current, the differential current is now increased to 0.12 amps in this case. Now, because of which there will be a voltage drop of around 240 volts. Now, of course, this voltage has crossed the threshold point, threshold setting of the relay. So in this case, the relay is going to trip all the breakers in the system, right, to clear this fault. So this is how the scheme will behave for different scenarios of external fault or internal fault or even nominal load condition. Now let us move on to the PVD relay testing part. So what I have here is the PVD relay nameplate. So of course we need some information from the nameplate, so we make sure we get the right model information. The type is PVD. Like you see here, it's a differential voltage relay, right? And the continuous voltage rating on this relay is 150. So here is your instruction leaflet information. So this slide shows the internal connections of this relay. So this relay basically has 2 operating units. So the first one is the 87L, as you can see here, and the second one is 87H. So the 87L unit, it is the instantaneous voltage unit, which has a high impedance operating coil connected across a rectifier here. So the purpose of this unit is to allow designation of the minimum internal fault that will operate the relay. So this guy is the one who first comes into picture whenever there is an internal fault or even external fault that actually decides, okay, this is the minimum amount of internal fault that I'm going to operate at. So the second unit is the 87H, which is an instantaneous overcurrent unit with a low impedance operating coil connected with the thyroid resistor stacks. So the purpose of this unit is to provide instantaneous operation for a severe internal faults, high internal faults. So both these units are connected in parallel to all the CTs secondary in the protection scheme. Like you see here, we have the contacts to monitor the 87H and 87L. And also here are the link positions for the 87H. So based on how you have the link set up, there are different ranges on the relay for the settings that you can choose from. And based on the way these links are set at, that will define your settings of the relay. So here are a couple of tests that we need to perform to be able to validate those two units that we just discussed. So here is the 87L element pickup test. The second one is the 87H element pickup test. Okay. Now we'll talk about test connections. So before we talk about this test connection, let's just go back for a second here to the internal connections. So to validate this 87L, we need to be connected between 5 and 6, right? So we make sure that we see that here, right? Between 5 and 6 for 87L, and for 87H, it's between 3 and 4. Of course, it all depends, the range of setting depends on the way you have the link positions set. And of course, we have the 1 and 2 where we can connect to monitor these contacts. So now we know where to make the connection. So we'll go ahead and now look at the connections again. So I'm using SMRT46D test equipment today to perform this test. And as you can see, I have my current channel 1 connected to 3 and 4, which actually injects the currents to the 87H up unit. And I have my voltage channel 1 connected to 5 and 6 that actually injects the voltage to the 87L. And I am using the binary input 1 in my case to connect 1 and 2 to monitor the trip contacts, right? Of course, you can use any of these binary inputs. I've just chosen the first binary input in my case. So let's go ahead and go to the RTMS and look into the test itself. So here what I have is a template that for a PVD relay. And let us go and take a look at the settings first. So here is the settings screen. So these settings were made for this template. So it has the model information, all the information that you got from the nameplate, that you got from the looking at the links on these operating units to get the actual setting. You can have asset ID. You can customize the screen as to how you would need it. So here's the instruction booklet, and if you have a particular phase you want to associate that relay to, of course, this is a single phase relay. You can choose that particular phase here for your reporting options. And we also have a percentage tolerance field here. So again, we usually provide up to 10% of tolerance for electromechanical based relays. But again, this depends on your testing protocol, like your company's protocol, and also you would have to look into the manufacturer's recommendation. But here is where you can change that so it reflects on the report. We have the position information of the links. And now here we have the settings that we're going to validate. So 190 volts for the 87L and 8 amps for 87H, right? And the target setting of 0.2 amps. So you can actually customize. I said you can customize the screen. So if you want to edit something, you can always go to the edit mode and change these here by clicking on this 3 dots here, and you can edit this particular setting. If you want to change the range here or change the default, you can do that here on the back end. Okay. So now that we have got information on the settings, we'll go on to the test. Of course, by clicking this button, you can either add or remove the settings from the report. Now let's go and look into the test. So you will need to navigate to the predefined test list when you open a template, so you can take a look at the list of tests that are built for that relay, right? So I have these two tests in my template that I'll be running the tests for. Let us choose this 87H current test, right? And I'll navigate to the notes section just to make sure we go through all the notes before we start testing the relay, right? So here, it tells us what are some of the general notes from the manufacturer, and what currents must be connected, and it tells us that these are the terminals that needs to be made the connection with, and the relay contact sensing is for the binary input 1 is used across the terminals 1 and 2, right? So we just come here, make sure it all looks good. We made the right connections. So here I have this display on run. So you can display this notes information for the user, if he's the new user to the software or this type of relay, so they can see this connection information when they run the test. So let's go ahead and look into the test screen as to how the test is built. So this test is built by using the ramping feature. Like, because this is a instantaneous over current unit that we are testing, we are using the current amplitude, and I chose channel 1. It's a single phase relay, and because it's instantaneous, I'm using a pulse ramp that is selected. From the setting, we know that the expected trip point is at 8 amps, and in my pulse characteristic, it starts at 85% of 8 amps, goes all the way to 120% unless the relay trips before, and the pulse increment is at 0.1 amps. Okay, these are the times when it pulses and it pauses before the next pulse. And as you can see, I'm using the binary input 1 for monitoring. So let's go ahead and run the test. So as you can see, it's pulsing at 0.1 amps for every 100 milliseconds, and it's waiting for relay to trip, right? So the relay just tripped, and it says the ending ramp value is 7.7 amps. Now let us go ahead and take a look at the single page report view. Right? So here, it says the sub pickup is 7.7, my expected is 8, so we are still good. The test passed because our percentage tolerance was 10%, and our percentage error was around 3.7. Right? So this gives a single page report view. This is not the whole report yet. Now let us move on to the second test, which is the 87L voltage test. Okay. Again, we'll come to the notes section, make sure we got all the connections connected accordingly, and then we'll go into the test screen to look into how the test was built. Now, when we were discussing about the internals of this relay, we did see that, again, this unit is an instantaneous voltage unit, right? So we chose voltage amplitude and V1 again because it's a single phase relay, and I've chosen the pulse ramp option because it's instantaneous. I would like to pulse the voltage. And from the settings of the relay, we know we need to be expecting the relay to trip at 190 volts or around. So we set it accordingly. This time we would want it a bit faster, right? It's around 2 volts increment per pulse, right? So at every 100 milliseconds, it will increment at 2 volts. So let's go ahead and run that test as well. So when you run the test, you see that the voltage 1 is incrementing 2 volts rapidly. It's pulsing and waiting for the relay to trip. So the relay tripped and it stopped at 188 volts. Right? So let's go look at the single page report view. As you can see here, the 188 volts is the result, the actual pickup point. The expected was 190. We are still good with the percentage error that we got, and the test has passed. So basically, we validated the both the operating units on the relay. There is a couple more tests that some of you might perform, the thyroid test and the target and sealing test. The target and sealing test is most commonly done for all the electromechanical relays, especially the induction based and the plunger type relays. The thyroid test also can be performed, but today I'm just going to I just concentrated on these two tests pertaining to the bus differential element testing. Okay, now let us take a look into the report. Now that we have performed these tests, so we have, here is the report with the past test status. We have the settings that is displayed, and both the tests that we perform, right? we can of course print this report in a PDF form. Of course, what you can also do is if you're creating this module from the scratch, or if you're using this module and customizing that, you can save this as a template. And once you save it as a template, you can use this on the multiple PVD relays. The same template can be used, right? So next time you have to run a test on a different PVD relay, let's say it's a B phase relay, all you have to do is open the new form of a template, right? And then just change this B phase and make sure that all these settings are matching that particular relay, and the tests are already updated with that particular settings, because we map these settings to the tests that are built in the template. And that is how these settings are used in each test. So that concludes the testing portion. Let's go back to the presentation and wrap up with this summary here. So today, what we discussed is David went over the transformer differential protection, the operation and the principle. He also discussed about how the scheme behaves for an internal fault and an external fault. And we discussed about the slope characteristic. We defined the slope characteristics and discussed about the harmonic restraint testing. And David did show how you can use the RTMS template, the BDD template, to test that relay. And then we saw the basics of the bus differential protection, and specifically we did discuss the high impedance bus differential theory. Like I gave you some examples on the scheme behavior for different scenarios, like the external fault and the internal fault and so on. And finally, we did see how you can use the RTMS template to test these relays, the PDD and the PVD. So that concludes the presentation portion.
All right, thank you, Sagosh. So as we conclude the presentation portion of the webinar, we're going to jump into our Q&A session so we can answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close your webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's a field where you can also request a quote or a demo of any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar, How to Perform Power Factor Testing with Megger Delta 4000 Instrument. The presenter will be Charles Nybeck. All right, let's get to your questions. The first one I have is for David. David, how often should the transformer differential relays be tested? Yearly, biannually, every 5 years? What would you say?
Okay, so on the transformer differential relay, it just depends, right? So there's a number of different ways to go about looking at this. Electromechanical style relays, in their the manufacturer's IL, they always stated, when in IL I mean by instruction leaflet, what they usually state is annually. Now that times have changed from when those were created till now, we have other governing entities at, say the utilities or some type of government entity, NERC, FERC, things like that, here in the States that actually dictate a little bit more of the maintenance schedules. So those the electromechanical relays that we used to do every year are now actually getting pushed out as far as doing the maintenance testing. It's kind of there's a lot of discussions that go on about this. There's a lot of things that happened in conferences and other areas that gather this type of information, like IEEE standards here. They'll dictate kind of what you need to do. You need to set up some form of maintenance plan for your system and just stick by it. If you see that your relays are not as good as they were a year ago, if you test a few a year, get a good test on those, and you notice that there's not really a huge amount of drift or calibrations that are needed, then you might be able to extend that time, but that is totally upon you and the information that you find out from your testing practices. So I would highly recommend going back and looking at your previous tests, and especially if you have older style relays, and then kind of trend that data a little bit to kind of know when you need to start looking into your devices and your relays and all these items, because they all play an important role to keep them calibrated on a scheduled time. Another good thing I like to bring up too is when I worked for the utility, we always tested the relay after a fault happened in that circuit. So if there was a fault out on a breaker or on the bus or transformer, we immediately test the relays. So that would actually take part of one of our testing intervals. It would, if we had 1 year to test, and then we came in and it was a fault 6 months into that year, then that test would happen that day. It's getting 2 tests essentially. It's getting one that's an actual fault that's on the system. Did it do its job? And then you go to the next one where you're actually doing the maintenance tests, which you can turn right back around and test it there, and then extend your timeout a year from that point. So it's a little different for different areas and different customers and users and so forth. All right, sorry.
All right. Thank you, David. Our next question I'm going to direct to Abel Gonzalez. Abel, what is the risk of setting pickup and trip threshold to the same value or threshold?
Hi. Well, we're talking about 2 different things here. The first is when we are talking about the pickup, is the minimum value of the operating variable that we need to reach in order for the function to either start timing or to realize that it should do, let's say, something. Let's take a overcurrent protection, for example. If you say that your pickup is 1 amp, then you need a minimum of 1 amp to either trip or start timing, depending of if you have a protection function with an unintentional or with no intentional time delay, or if you have a timed overcurrent function. Now, the threshold that we're talking about is how much does that magnitude need to drop before we declare that that function is no longer in pickup. Now, every protection function will have a threshold between the pickup value and the moment when we declare that, let's say, dropout of the pickup magnitude, that is not, it's never going to be 0. So you can never choose, or you shouldn't. I mean, I don't like to say you can never, because you can't. Maybe you can do it, and but in my opinion, it would be wrong. And relay manufacturers, they simply either do it by default and they declare it in their, let's say, documents or their user manuals and whatnot. And in some cases, for particular functions like frequencies and stuff like that, they will give the user the ability to select that that threshold. But the thing is that if you choose the pickup and that threshold of exactly the same value, then you will have oscillations that happen naturally during the measurement. The current is never, actually, the probability of a current being 1 amp is 0. You have some probability of the current being between 1.0000001 and 99.9999999, but the probability of being actually 1, is, you can say that it's actually 0. So you never choose that threshold equal to the pickup. You always choose a little bit of a let's call it the security band. In some protection functions, it's called a hysteresis, which means that you need to go either the pickup plus the threshold, or the pickup minus the threshold, in order for the function to deassert. So the risk of setting it at the same value is that you will have a rattling on the binary outputs, and you will have an uncertain operation of the function. That's what I would I guess answered.
Thank you, Abel. All right, excellent. David, next question is going to be for you.
Okay.
Can I utilize multiple SMRT1 units or Smart 1 units together to carry out differential relay testing, or do the three-phase units need to be utilized?
No, you can use 3 Smart 1s. That is absolutely correct. You can use the Smart 1s, and you can test the relay. If you have a BDD relay, you can use 3 Smart 1s or even 2 for that guy. You also have the, you can use for electromechanical style, a good 2 units, SMRT units can be utilized. If it has a 3 winding in there to make life a little easier, you can definitely use all 3 and hook up one time, daisy chaining those units together. When you do a microprocessor based transformer differential, you can still test it single phase unless you have elements in there that are required for 3-phase testing. And it all depends on how you want to test. But yes, you can use SMRT1s tied together, and you can use those to test differential relay. I will also even go even farther than that to say if you had 6 Smart 1s, then you can do in relays that have the 3 winding input, you can actually run all 6 currents, 3 from the high side and low side of what would technically be in the relay, your primary and secondary side in the relay as well. So you can actually run 6 units and run a full scheme test there also. So there's a lot of flexibility with the Smart 1s, and there just about isn't anything that you can't test with a Smart 1 when you have the flexibility of tying them all together. Also, to end on this note, the Smart 1s can also be daisy chained to the 3-phase units. So you can also have a 3-phase unit, and then if you need a couple extra currents just to do some different style of tests, then you can actually daisy chain those Smart 1s to the 3-phase units as well. So you have a lot of options there, but yes, in the end, the answer is yes.
Thank you, David.
Yeah.
Our next question is going to go to Sugosh Kuber. Sugosh, even though differential protection operates in current, why use a high impedance relay with a voltage element?
Yeah, that's a very good question. So, like I mentioned before, I in today's webinar, I explained about the high impedance bus diff. There is also something called as low impedance bus diff, where it works on the principle of current, right? Only it does not use that voltage that we discussed now, and it's similar to the principle that David explained about the operand restraint quantities today. So even that scheme calculates the operand and restraint from the currents that it is measuring from the CT secondaries, and then decides whether the fault is internal or external. Now, so there are some of the reasons why why voltage is used and why the scheme is sometimes preferred. Of course, this depends on the applications that you want to implement these type of schemes. So with respect to the voltage-based scheme, right, you don't have much complexity with the settings. But however, if you talk about the low impedance scheme, which is the current based, you would have many number of current inputs. Again, you would have to use all those secondary current inputs in the relay for calculation. However, here, based on the current that is being forced in the measuring path for the voltage scheme, it just measures the voltage across the relay. So when we talk about the setting complexity, voltage-based scheme is a bit lower complex compared to the current scheme. And also, like if you are doing the installation, the wiring complexity is the voltage-based scheme is lower as compared to the current-based schemes. And there are many other reasons. Of course, there is nothing like advantage or disadvantage. Again, it purely depends on what kind of application you want to implement the scheme set, and also like what type of installations and your scope of logistics as to what kind of relays you're using for the scheme and things like that. So.
All right, thank you, Sugosh. Abel, could you elaborate more on the linear coupler used in bus protection?
Sure. Well, I don't know if I start at the beginning or at the end, but I'm going to say that a linear coupler is, I would say, and I was writing that just a while back, a cute name used for air core current transformers. Now, why do we use those in bus differential protections? And the reason is that if you guys remember your power systems, you know, faults and how and what was the characteristic of power system faults, you remember that in every power system fault, or in most single phase power system faults, and even in 3-phase ones, you have a DC component. Now that DC component dies out after a few cycles or a few seconds, and it depends, and how fast that depends on the time constant of the circuit at the point of the fault. Now that DC component takes a longer time to let's say dissipate or be eliminated. When you are talking about bus faults, that DC component has a very long decay time. Now, why is that DC component important? Because current transformers, they saturate because of let's say mostly two different phenomena. The first one being how much voltage is connected to the secondary of the or injected to the secondary of the current transformer. Now that voltage is the product of the current that circulates through the secondary times the impedance connected on the secondary. If we are using a current transformer in a high impedance bus differential protection, then there's going to be by design a high voltage on the secondary of that current transformer, which will tend to saturate the current transformer. The second reason why current transformers or any core saturates is when we use a direct current component to the current that circulates on that current transformer, which means that we are talking about two reasons why current transformers saturate, which are present in bus differential protections, which is what we have been talking about. Now, a linear coupler, as I said at the beginning, is a name for a air core current transformers. And their air core current transformers, since they don't have magnetic component, they're very hard to saturate. They have a much more linear response, which means that they are more suitable for this type of application. And that's why we use linear couplers in bus protection, and we don't use them in other applications in the system.
All right, thank you.
That's it. Sorry.
All right, good deal. So, David, next question for you. For maintenance planning, what is the expected lifetime of the differential relays such as electromagnetic solid state and the like?
So in the lifetime of a relay, that all depends, and it all depends a lot on how it was treated, what the elements are, what environment it was in. It depends on a lot of issues, especially in testing. What a lot of technicians have issues and come across with relays not lasting is because sometimes they decalibrate a relay to recalibrate it. So you know, once you put your hands on it and actually have tweaked and turned and done a few things, then the life expectancy of the relay could be anything, you know, really. So the best answer I can give for this is to talk to the relay manufacturers, ask them what their the life expectancy of the relay is and what those conditions need to be if you were to apply your maintenance test plan or maintenance program to this relay, and they can give you a little bit better answer on the life expectancy of particular style relays. But again, that's, you know, that comes into a whole wide range of items, because, you know, are they outside? Are the relays outside in the breaker cabinet? Are they inside? Are they, you know, been in the nice air conditioning? Are they been in a hot control house? You know, a lot of the elements actually affect it. And then two, a lot of other things that I've seen as well is just being maintained poorly. It could really affect the relays, and not only the operation, but or not only the life expectancy, but also the operation of the relay as well. So I would just highly encourage to talk to relay manufacturers and see what their recommendations are on them, since a lot of them have seen a lot of their old equipment come back in for repair, come back in to have it calibrated or reconditioned, and just kind of talk to them a little bit and get their feedback on what they have and what they've seen. And it kind of helps you out determine how long you want to keep your relays, or how long you need to change them out or test them or so forth. So they can give you a lot of really good information and data on the life expectancy. So it's actually a really good question.
All right, thank you, David. Sugosh, this equipment is performing secondary injection. So is it testing only relay functionality? Is it possible to make primary injection as well?
Okay, yeah, I mean, yes, the way we tested right now is we tested the functionality on the relay by mimicking, external fault and internal fault, making sure that settings on both those operating units were validated. Um, so let's say if you want to perform a primary injection test, so there are many factors here now. How many CT buckets are present in that for that particular bus, right? Because you would have to inject the currents on the primary side, and now, of course, you could have multiple units daisy chained and have single phase currents injected on each of these CTs that are present in the scheme, but you would require multiple test sets depending on your current needs. Of course, you would require the test sets, the right configuration of currents on the test sets, and also many leads for your test setup. So it totally depends on your on the logistics as to how many CTs are present in the scheme. But if you have the right equipment and right set of planning and the tools, you can also perform the primary injection as well.
All right. Thank you, Sugosh. While I have you, I'll ask you the next question as well. Can you talk a bit about testing a low impedance bus diff element?
Okay, yeah, like I was talking earlier about a bit of comparison between the high impedance and the low impedance type of schemes. So as the name suggests, the low impedance, this type of relay has low impedance to the flow of the secondary currents. So basically, the currents that are seen on the secondaries of the CTs, this type of relay, it calculates an operating quantity and a restraint quantity. Of course, the equations are different. So it vectorially sums these currents for the operating quantity and just sums the magnitude portion of these currents for the restraint quantity. Now, like similar to the transformer diff protection that we saw earlier, you would have a slope setting in the relay. And anytime the ratio between these two quantities, the operate and restrain, that resultant goes above that slope setting threshold of the relay, then it means that the relay has seen internal fault and it will operate. So that is the basic idea behind the low impedance relay, low impedance bus diff relay. And when you have to perform testing on these relays, usually these relays have multiple CT inputs coming into the relay. So you would want to make sure that you have the right type of test equipment, the right model, which will give you many currents. For example, SMRT 410 can give out 10 currents at one time. So this type of scheme requires a lot of currents. So as long as you have all those right currents set up, you should be able to test these. You can validate the slope setting by calculating what amount of operate quantity and restraint quantity needs to be come up with, and for that you would have to inject those amounts of currents.
All right, thank you. My next question is going to be for David. David, how do you account for the phase shift of a power transformer with electromechanical relays?
So when electromechanical relays don't have the smarts built into them for calculating the compensation needed for a delta Y delta transformer. So what we have to do is you have to connect externally CTs to these. Sorry, let me back up. So you have to connect the CTs secondaries to the relays with the phase shifts taken out of them. And what I mean by that is if you have a Y side primary and a delta secondary, you're going to have a phase shift between just the transformer from the high side to low side. Now, in order to compensate for that, then your CTs on your primary side are going to be wired delta on the Y side of the transformer, and then it's going to be on the delta side of the transformer, it's going to be wired in Y. And that essentially cancels out the phase shift, and you can wire those directly to the back of the relay. And that's how we will get the phase shift taken out of that circuit when you're crossing through the transformer. And I am talking about transformer differential here because we would always have some type of compensation between high side and low side. Now, if your transformers are YY or delta delta, or they're the same from the primary to secondary side, then there's no phase shift needed, and you can wire your CTs accordingly. But that's how we would do that. Yeah.
Thank you, David. Additionally, how do you determine minimum pickup of relay windings?
So on the relay windings, I will use the transformer diff as, because we talked about it, I will use it as an example. So when I was saying earlier, the nameplate, electromechanical based relays a lot of times have the pickup values put on they're printed on the front of the nameplate. Right? So even if they don't give you the actual pickup value, they're going to give you a percentage of what the tap needs to be, or some small fraction of what the minimum pickup setting will start at. Sometimes, if this isn't a perfect world, I've been spots where they didn't have the nameplate even on the front of the relay. So at that point, you need to go to the manufacturer's IL instruction leaflet, and you need to see what the information is for the pickup and how to get that pickup value as well. So if you're in a GE, an old electromechanical GE, usually all the information's in the front of the manual. If you're in an old ABB style relay, then the information that you need is in the back. So a lot of that information is in the manual. Even if you're doing microprocessor-based relays, all those calculations and how they're getting those pickup settings are in that manual as well. They're not easily printed on nameplate because it's a huge relay, but at least it has lots of elements, but you can actually get all that information out of the instruction leaflet.
All right, thank you, David.
Yes, sir.
It looks like that's all the time we have for Q&A today. We apologize if we didn't get to your question online, but we will be trying to follow up with you offline in the following week. A copy of these presentations, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great week.